So privacy is a concern, right? So it's everywhere. So like in the United States, you have Facebook, Meta, Google collecting tons of data. Here, you also have other, in China, we also have other privacy issues. So it's a global issue. Okay. And I think there's no need to motivate the issue of privacy. And it's not that working, actually. Yeah. And nowadays, because of the generative AI wave, the privacy issue becomes even more apparent because these models are trained on tons of millions, billions of personal data. And I guess everyone you have already contributed your data to the training of these big models, large language models. So they know much of us. Also, people may use alignment to let the language model not to release your personal information, but most likely they internally know what you are, who you are. So it's very concerning. Yes. Okay, and there are some ad hoc approaches to improve privacy. For example, the simplest way is to delete your names, to make it anonymous. So this is the Netflix competition. So and everyone, based on some Netflix data, everyone can rate your movies. So they are the people. So, but however, people invented an algorithm which relate multiple data sets. Okay, in the sense that in this data set you don't know this is a Hillary Clinton, but her record may also appear in this data set. And by relating across different data sets, we can identify some unique person. So that's an algorithm. Okay, this means that it's impossible to protect privacy by only removing your name. The idea is basically we have our names on records on multiple data sets. So as a result, the Netflix competition was canceled because of lawsuits. And in biomedical research, and it's a practice to release the average minor allele frequency. Okay, so basically, what's the average frequency of this gene across 1,000 people? But based on these simple vectors, so this is summary statistic, we can uniquely identify where you are, whether you are in the data set or not. Okay. So as a result, and this kind of releasing data is forbidden to release later. So it's the end. Seems it's the end of privacy. We have to sacrifice our privacy rights in this modern life. But good thing that for computer scientists, since at work, who was my mentor, I spent a summer internship with her at Microsoft Research exactly 10 years ago. So since then, she has been my mentor for always. And so that's why I entered into this field. So since at work, Frank McShaffey, Colby Nassim, and Adam Smith, 4 computer scientists, introduced the concept of differential privacy. And later on, we realized that this is actually related to hypothesis testing. Okay, so what's the rationale about differential privacy? The idea is that so this is the common part. Okay, they are identical between these 2 databases. They are the same, but we don't know whether the last person is Alice or Hua Mulan. We don't know. So we want to ensure that no matter it's Alice or Hua Mulan in the dataset, based on the outcome from the algorithm, okay, we cannot say much about whether it's Alice or Hua Mulan. They are very similar. So that's the idea. Okay, so that's what we want to achieve for differential privacy. And the typical setting in differential privacy is as follows. You have multiple records. Each record corresponds to a person, like Alice, Bob, Charlie. And so each column is there some information like gender, age, salary. Maybe for gender, it's not that sensitive because you can know, you know it, right? You can, but most of the time. Yeah. But salary might be very sensitive. But in differential privacy, we cannot release the exact average salary. So the idea is that you need to introduce some noise in the form of randomization. This randomization should be large enough to to hide whether it's Alice or Hua Mulan. But of course, the noise should not be too large to hide the population level information. So there's a trade-off. Okay? Trade-off. Meanwhile, you want to maintain the prediction power, but of course, you also want to hide some individual level information to protect privacy. So this is the setting. In differential privacy, we have two realities. One reality is Alice in the dataset, the other is Annie. But for the other, Bob, Charlie, Dave, they are the same. There's no difference. And based on the outcome of the algorithm, we want to decide whether it's Alice, whether it's S or S prime. So there are two hypotheses. So there's competition between these two. Okay, and under the null hypothesis is Alice, on the alternative is Annie, but it's slightly different than hypothesis testing in statistics, because here we assume that H0 and H1 are symmetric. There's no difference between them. Typically in statistics, null and alternative are different. They are not symmetric. They are not exchangeable. Okay? So the idea is that if this is difficult to do hypothesis testing, in the sense that both type 1 and type 2 errors cannot be small at the same time, so then privacy is preserved. So this is the key idea about differential privacy. So differential privacy now got very popular in real industry level, like Google and Apple this time. And so this is a real screenshot from my own iPhone. Like several years ago, when iCloud asked me to upgrade my iCloud, and they say whether you are happy to submit your data to Apple to analyze your data, but they will preserve private differential, use a technique called differential privacy to preserve your privacy issue. Okay, so this is my field. I feel very excited. I press yes. You analyze my data using differential privacy. And so this is for computer science scientists propose differential privacy, and Cynthia was my mentor. It's my mentor, sorry. She is always my mentor. And it had always been a dream for everybody working on differential privacy that Cynthia, the work will receive a Turing Award sometime. We think it will come someday. So every March, I will pay attention to the Turing Award. Unfortunately, this year it's not, but I think she should get the Turing Award at least within the next 3 years, because this is a real impact. Okay, real impact. Some idea from theoretical computer science, particularly in crypto, but got impact in machine learning, statistics, and artificial intelligence, I think. Okay, and what's new in this talk? So far, everything is old, like very old. So this is some reference which our talk will be based on. In particular, it's mostly based on this paper, because this is a paper which has the honor and also luck to receive the ICBS award yesterday. In particular, so Jing Shuodong was our student, and he basically leads the force of this paper. And so now let's compare what is F differential privacy, which will be proposed in this talk, and the original epsilon delta differential privacy by Cynthia Dwork et al. Okay, and first of all, they are very similar in the sense that we are both interpreting hypothesis testing using they are both interpreting privacy using differential privacy. So that's why we all call it differential privacy. We are all differential. Okay, differential privacy in Chinese called 差分隐私. So 差分 or differential is the key thing. Okay, but we are using the type 1, type 2 errors trade-off to measure the privacy. Okay, how much privacy is there? But epsilon delta are using the worst case likelihood ratio. As a result, we are using a functional parameter which maps 0, 1 to 0, 1. But in epsilon delta, they use epsilon delta 2 parameters. Okay. So what's the typical way to treat privacy? In our setting is to add Gaussian noise. But in epsilon delta, is to add Laplace noise. Okay? So there's comparison between the two. Okay, a very early preview of FDP. I so far haven't introduced the definition, but I can tell you that FDP is the only one to satisfy these 3 desired properties at the same time, namely informativeness, composition, the subsampling. It's not only about epsilon delta, and there are many differential privacy definitions. Mostly are based on divergence between probability distributions. Okay, it's a zoom, but the FDP so far is the best. It's only one to satisfy all the three. Okay. So what is informativeness? Roughly speaking, we have to use the privacy definition. The measure should describe the privacy in a lossless manner without losing any information. But all the divergence, especially random divergence-based differential privacy, will lose some information. Okay, and what is computation? Computation is that you analyze your data multiple times, right? For example, ImageNet. ImageNet is basically build the foundation for modern artificial intelligence. It has been analyzed by maybe 1 million times, because there are 1 million papers in deep learning, right? Every paper is based on ImageNet. So as you analyze the data more and more time, you will release more information from it. Okay, so privacy will decrease. How much and following what principle will privacy decrease is a key issue. But however, Epsilon data is not doing this very well. Okay, last is subsampling. Okay, and the subsampling means that you don't need to have all the data. Sometimes the database is too huge, and you only need to have to sample only 1% of your data from the database. In this case, 99% of the time, certain individual will not appear in your analysis, so privacy is preserved. So there's more privacy because of this. And but however, random differential privacy, random divergence-based differential privacy does not do this well. Okay? So now let me introduce FDP. What is FDP? First of all, we need to introduce trade-off functions between two hypotheses, between two probability distributions. Okay. Again, this is a setting whether we are asking whether it's Alice or Annie in the data set. Okay. And now we use a rejection rule to do the hypothesis testing. Rejection rule means that if this is 0, means I choose P. P is a probability distribution of the, say, noisy salary. If this is Alice, okay, Q is a probability distribution of the noisy salary if this is Annie. And if you choose 0, you will accept the null distribution. If you choose 1, you will reject null. You will choose the H1. And sometimes it can be between 0 and 1. Then you have to do a randomization. So there's type 1 error, type 2 error. Type 1 error is a probability that in reality it's P, but you reject the null. And the beta is the opposite. It's type 2 error. Okay. And now we can define the trade-off function between two probability distributions defined on the same space, which is the given any level alpha between 0 and 1. And this is the smallest type 2 error, such that the type 1 error is controlled at alpha. The best rejection. And this can be achieved by the Neyman-Pearson lemma. And there is a mathematical characterization of a trade-off function. It's only if f is convex continuous, non-increasing, and the last is below 1 minus alpha. Okay, so this is a definition of FDP, and this definition says that this is FDP if and only if for this algorithm, the trade-off functions between two neighboring data sets. Neighboring means that they only differ by Alice or Annie, and the type 2 error is bounded below by f at any alpha between 0 and 1. So having a large type 2 error on the left means that this is more difficult to tell apart Alice or Annie, right? So it's more difficult. So this means that there's a lower bound for you, for your ability to distinguish between Alice and Annie. So the privacy lower bound is given parameterized by f. Okay. So far, yeah. By the way, any questions so far? Any question? So f is a parameter, and typically f is another trade-off function. So as long as this is a continuous decreasing convex and below 1 minus alpha. It maps any number between 0 and 1 to another value between 0 and 1. Okay. Okay, so this is the definition of epsilon data. But roughly speaking, this says that the likelihood ratio between S and S prime is uniformly bounded by e to the epsilon. but with some slackness delta. Okay. And here, so this is a mathematical equivalent. So M is absolute delta if and only if this is also FDP, but this F is given by this very weird trade-off function. Okay. So this is 1 minus delta, this is 1 minus delta. Okay. Very weird. And this motivates our work because why it's the trade-off function looks so weird. Okay. So in general, the trade-off function should be ending convex function, right? Convex function, but this is a very weird function. Okay, so now F is too general. Now let's introduce a subfamily of probability distribution. So this is the Gaussian trade-off function. The Gaussian trade-off function is parameterized by a single parameter, which is the trade-off function between standard Gaussian and the Gaussian with mean mu. Okay, and so this, which means a closed form expression. Phi is the CDF of standard Gaussian. So this is says that the trade-off function between any two neighboring data sets should be lower bounded by G mu. Then we call it mu GDP. And so this is also FDP, but the trade-off function takes a special form given by a single parameter. Okay, and later we will see why this is important, and because of the central limit theorem. But now let's take a look what that looks like. And when mu is 0.5, it's here. So it's not, by the way, here it means that your type 1, type 2 error add up to 1. This means that you are deciding whether it's Alice or Annie by tossing a coin. So there's no way for you to gain any power to break their privacy. The lower, the less privacy. Okay? When mu is 6, there's no, actually it's here. There's no absolutely no privacy at all. Then how can we achieve differential privacy? Okay, and in computer science, people have invented millions of ways to achieve privacy. But a typical way to achieve differential privacy is by the template, by adding noise. Okay, somebody wants to understand what's the information, for example, information of the data set in the form of theta. And but as a curator of the data set, you cannot release the information directly. You have to add a sort of noise. What kind of noise do you need to add? Depending on how much sensitivity your function theta is. Okay, the sensitivity means that the largest perturbation you will see S and S prime if they are neighboring. Okay, for example, if you are counting the average salary, if someone like Bill Gates or Elon Musk is here, and okay, whether he is here or not will make the average salary change so much, so there's not much privacy, right? So that's the intuition. And you have to add proportionally noise proportion to the sensitivity. Okay, sensitivity. Gaussian noise, and yeah, it's very simple. It's basically I would say high school maths. Okay, and now let's introduce informativeness. So this is based on Blackwell theorem. Obviously, this is the single most important theorem in this slide. And so basically, we say P prime, Q prime is a Blackwell harder than PQ if P prime or Q prime is given by some deterministic, or in some sense actually can be random, processing of the original P or Q. So this is essentially the Markov kernel. Okay, for example, this process can be a dimension reduction. Okay, you basically can throw out some information in P or Q. Since you throw out some information, and then it becomes more difficult to distinguish between P prime and Q prime, making it more difficult for you to distinguish between the two. And the Blackwell theorem, which was proposed 70 years ago, says that the trade-off function actually dominance between trade-off functions is exactly equivalent to the dominance of the Blackwell hardness. They are mathematically equivalent. Okay, so this shows that in some sense, in mathematical rigorous sense, if we want to preserve this privacy comparison P prime Q prime and between P and Q, we have to use the trade-off function. Trade-off function is the one which provides all the information for you. Okay. So by the way, maybe what is Blackwell? Blackwell is called David. He is David Blackwell, who was a professor from Berkeley. He was the first African American who received a doctor's degree in mathematics, first one, which is remarkable. And so this year, NVIDIA released their next generation GPU platform, which is named after David Blackwell. It's huge. It's a huge impact. Okay, and now let's introduce Renyi divergence, because there's a lot of differential privacy definitions based on Renyi divergence. Okay, so this is Renyi divergence of order gamma. Any order gamma larger than 1 can be defined. When gamma is 1, this is a KL divergence, which is very familiar to everybody who works on machine learning. Okay, and there are all these differential privacy definitions are based on this Renyi divergence. Okay. And however, there's a counterexample. So this is the Bernoulli distribution P epsilon Q epsilon. And we can prove the following results. Okay, for Renyi divergence for any order will think that the Bernoulli distributions will be more private than these normal distributions uniformly for any order larger than 1. Okay, so in the sense of Renyi divergence perspective, the Bernoulli distributions have more privacy. But however, for total variation perspective, this is another divergence, okay? And this will be the opposite. The total variation distance will think that the Bernoulli distribution will be less private than the normal distribution. This contradiction is not a mathematical contradiction. This contradiction is only because this comparison is not complete. Okay, Renyi divergence is not complete. Renyi divergence is lossy. So this is not the case for trade-off function. If the comparison between trade-off function is uniformly for any alpha between 0 and 1, then any data processing preserving divergence will say the same comparison, will have the same comparison with the trade-off function. So there's no contradiction at all. Okay, so this is a mathematical condition, mathematical statement. So now let's move on to computation. And in what is computation, as we said earlier on, based on your multiple analysis of the same data set, you will know more information about this someone in the data set, right? Privacy will degrade. And how much privacy degrade now is a subject here. So we have to introduce, for example, 2 algorithms, M1 and M2. M1, so here M2 can depend on not only the original data set, can only depend on the outcome from M1. Okay? Because the paper based on M1 has been published, right? Now you are writing a second paper, so your paper can depend on the first paper. So that's why there's dependence. Okay, and you can do this computation for not only 2, 3, 4, all the way. Okay? And so here is a tensor product. So this tensor is not the mathematical tensor. Okay, it's only for fun, I would say. So here we introduce a tensor between 2 trade-off functions, which is the trade-off function between 2 product measures, P times P prime versus Q times Q prime. The intuition is that if this is Alice, and then the first component M1 will have distribution P, and the second will have distribution P prime. Okay, so that's why we make product. Okay, and mathematically, this operator is cumulative associative. Okay, no matter which one you do the computation, F, G, H, doesn't matter. And in the case of Gaussian differential functions, it's just the L2 norm. Very nice. Mathematically, it's very nice. Okay. And so here, this is basically kind of look like an algebra thing, because this trade-off function makes the computation complete. Because the computation of any algorithms will still be FDP, and this trade-off function will be given by these tensor products. Okay. So this is tight, by the way. You cannot improve uniformly. Okay. Now let's introduce this central limit theorem for FDP. This theorem doesn't look like central limit theorem, right? But the proof is actually is just based on the central limit theorem. So the idea is that now you have an algorithm, and for example, a deep learning, right? Deep learning algorithm, you want to apply the backpropagation steps millions of times, billions of times. Each time you release a tiny bit of information, and this is given by the trade-off function. Tiny bit means that the distance from the diagonal, okay, diagonal is very close. So this is very close, and the closeness is given by 1 over root k. Okay, if you are familiar with central limit theorem, I guess everybody does, right? And this is exactly what is the triangular, right? Triangular statement in central limit theorem. Okay, every step is very close to 0, but if you do the computation together, it will converge to normal distribution. Hi, please, Lin. Hmm? Yes. Yeah, it's always, I would say, it's always a lower bound. It's always a lower bound. So yeah, I see. Yeah, so when the definition involves the algorithm M, so for each algorithm, when we define the privacy, it's always a lower bound. But here, there is no algorithm. It's defined through their privacy parameter. So their privacy parameters, it follows this kind of identity, but it's not about the algorithm. The algorithm is still lower bounded by this trade function. It's still lower bounded. Yeah. Thank you. So the convergence is uniform between 0 and 1, and the mu can be computed by calculating the first and second moments associated with each trade function. So here the idea is very simple because this says that if you are dealing with a complex algorithm, which is often the case in deep learning, which can be decomposed to millions of small steps, and then overall their privacy will be modeled by Gaussian differential privacy. So this essentially provides a approximation tool, but because now you only need to evaluate mu. Mu is the parameter you need to care about. Okay. And so this is final sample approximation. And previously it's asymptotic. This is final sample. Okay. And so this is the computation for pure differential privacy. Delta is 0. So in this case, you see, if you want to exactly compute this thing, it's going to be Sharpie complete. Okay. What is Sharpie complete? This is not my background, but I have some theoretical computer science friends, and they told me that this is even more complex than MT complete. Okay, so I buy it. And okay, but interestingly, this approximation error looks like 1 over k, right? Because in probability, we know that there's a Berry Eisen bound, and which is tight in general. This tells you that for standard limit theorem approximation, the error is basically 1 over root k. So this is tight because this already holds for the Bernoulli case. But why do we have 1 over k? This is essentially because we are dealing with type 1, type 2 errors. And for type 1 error, if you want to get the exact type 1 error, you have to do randomization. This randomization will smooth out the 1 over root k gaps, so making it 1 of k. Okay, yeah, so I have explained. Okay, now let's move on to the third part. So third part is subsampling. So I still have like, because time's delayed, I have 15 minutes, right? Yeah, thank you. Thank you. Yeah, time is good. Yeah, so subsampling means that for any data set, I do not apply my algorithm to the entire data set. I only subsample from it, okay? Which is the case nowadays, because if you are dealing with some data sets is huge, right? And the ImageNet is the old time. Now we have people have more larger and larger data sets. And it's impossible to apply your algorithm on the entire data set, just impossible. So you have to subsample from it. And by subsampling, you mean that there's some probability, some chance that someone, okay, is not included in the analysis. In this case, this person's privacy is perfect, okay, imperfect. So here we want to understand how much privacy is enhanced by using this so-called subsampling technique. So here we have to introduce a bit notation, and M means that we only subsample M data points from a data set, original data set with n size. So this is a fraction P, which is M over N, is a subsampling ratio. And now let's define FP and FP inverse. FP is basically the convex combination with P 1 minus P. So the idea is very simple. With probability P, I still using the original trade function because you are included in the analysis. But with another probability 1 minus P, you are not included. In this case, your privacy is perfect. Okay? You lose 0 privacy. And here we have to make it symmetric. We have to use F inverse. And last, we consider the double conjugate to make it convex. Okay, because by definition, the tutor function have to be convex. So this theorem says that FDP, if the original algorithm is FDP, and then the subsumed algorithm will be this FDP by this notation. Okay, this notation will be. And now let's take a look at what this operator looks like. Okay, the operator looks like this. Okay, and for example, the original algorithm has this privacy bound. Oh, okay, this is the original F. By applying the operator above, now this looks like this. And what is the blue line and the red line? This is the original FP and the FP inverse. The double conjugate will basically give you the convex envelope. Okay, convex envelope doesn't change anything, only change this part because you want to make it convex, right? So otherwise it will be concave in this part. Okay, and so this is the original privacy analysis without using our FDP framework will give you this privacy bound. But our algorithm will have this analysis. So this improvement is given by our F-trade-off function framework. Okay, so we are done, and now let's try to make some application to deep learning. Okay, I think there's no need to motivate why deep learning is somewhere privacy violation is everywhere, right? I have to, whenever I have entered some places, someone will scan my face, okay? And so I know that someone over there knows where I'm at any time. Okay, it's a concern as basically deep learning. So Google Brain developed a private deep learning framework using their TensorFlow like 8 years ago. So this is basically the algorithm to achieve differential privacy for deep learning. So roughly speaking, so by the way, ICBS also gave the paper award this year to this paper, this paper. This paper is titled Deep Learning with Differential Privacy. One of the authors was my friend Li Zhang. I haven't saw him since I left Microsoft, and so I saw him yesterday. He also received the ICBS award, but in the computer science category. Okay, so this is the algorithm proposed in their paper. So roughly speaking, you have to do 2 steps. This is the truncation. If the gradient in deep learning is too large, you have to make it smaller, but we're keeping the same direction. And the next, you have to add some Gaussian noise to hide the individual level information. Okay, 2 steps. And now let's try to analyze this privacy definition, deep learning privacy using our framework. Again, this is joint work with my former students, Zhi Qipu and Jing Shu, and my colleague Qi Long. So, so the paper which received ICBS in Computer Science Award yesterday was deep learning with differential privacy without Gaussian. We changed only one word from their title. Okay, and it's not working. Oh, it's working here, but it's not. Yeah, there's some delay. Okay, so this is our analysis, and basically this allows why deep learning is a good application, because deep learning here both has subsampling and the computation. Subsampling arises because of mini batch. Each time you need to compute your gradient sampling from mini batch. So this is a optimization convenient, but practically the only approach, right? Because if you want to compute the whole gradient from ImageNet with 10 million data points, then it's impossible. You have to subsample like 200 data points to compute a gradient. Okay? And next is computation, because you need to repeat this for millions of times. So now, using the theorem for subsampling and the computation, we can get a asymptotic privacy bound, which takes this form. Okay, you see if the fraction is larger, and then there's less privacy because mu is larger. The larger mu is, the less privacy is. And also depends on t. T is the number of iteration. If t is larger, then you have less privacy. Also depends on noise. If noise is large, then this will be smaller. You have more privacy. So that's the story. Okay, and this is a comparison between our GDP analysis and the Google Brain analysis. Google Brain introduced a technique called the moments accountant, basically leverage the moment generation function. And our analysis is given by this red line. Okay, so again, the larger the trade-off function is, the better the privacy bound is. So we didn't change the algorithm. The algorithm is still the same, but we just get some privacy for free from the analysis. And the comparison becomes more apparent when the accuracy of the deep learning algorithm reaches 97%. In this case, this is our privacy bound. This is a Google analysis. So Google Brain will be very pessimistic, who might say that, oh, we have no privacy at all. But actually, our analysis shows that you are too pessimistic. So there's still decent privacy over there. Because here mu is just 1.13. So this is still basically one standard deviation. Not crazy, not crazy. Okay, and since we always get uniformly better privacy analysis, so this shows that if we want to reach the same privacy level, we can add less noise. By adding less noise in the deep learning algorithm, we can achieve better privacy prediction. We can achieve better prediction in the test domain. Okay, so this is our comparison between our framework and the Google Brain. Okay, and so again, the comparison is the same. With the same privacy budget from this level to that level, we uniformly improve the Google Brain's private accuracy. Okay, I think I'm almost done, and now let me conclude. So basically, we have shown that FDP, because the trade-off function is informative, and the computation is tight, and the subsampling, well, is also mathematically convenient and tight. And the last, it basically is the state-of-art application to deep learning, private deep learning. Again, so this is a triangle which summarizes this talk. FDP is the original of our framework. Epsilon delta is included as a special case, and GDP is a special case because of the Gaussian trade-off function family. But because of the central limit theorem, everything will converge to Gaussian differential privacy. So this is make me very excited because this brings Gauss back to our field. So my undergraduate major was pure math, basic math. But later on, I chose to do statistics and machine learning. So somehow I left was a little bit far from the math family. But this work made me realize that I'm still doing math, and I hope that everybody will still think that I'm within the math. Thank you. Oh, I see your question. So your question basically saying that, oh, in epsilon data, you are using Laplace noise or kind of randomization, different randomization. And the answer is that our FDP can also analyze this setting. So FDP is basically provides an umbrella for any privacy definitions. But under this umbrella, it says that Gaussian noise actually mathematically is more elegant. It's basically the right choice for adding noise. Laplace noise, okay, it also will give you privacy protection. But under this definition, this broad definition is not the best one. Yes. Oh yes, I understand. And so there's a trade-off, and rigorously speaking, in theoretical computer science, people are not happy with any asymptotics. And but for some applications, asymptotics actually will give you very reasonable approximation. So this is our case. And we have some following our work, which tries to estimate the remainder in the case, special case for the US sensors, which will be available perhaps next month. So roughly speaking, we are further expanding the Taylor expansion for the moment generating function using the Edgeworth expansion. Because central limit theorem is basically the first order expansion of the moment generating function. And we can further down the expansion to get more approximation. And this approximation will give you rigorous bound. Yes. Yes, thank you. I think it's a yes or no answer. Yes, in the sense that, yeah, you can achieve privacy by adding Gaussian noise everywhere in any procedure. But no, in the sense that this is an art. In computer science, there are like, I guess, 10,000 papers in differential privacy. And so this becomes an art, or kind of art, in the sense that under which the pipeline of the algorithm under which you should add noise randomization. And then you will overall achieve the best prediction power, because you don't want to ruin the algorithm's performance by adding too much noise. And so this is an art, I would say. There's no mathematical framework to let you know which is the best place to add noise. The Gaussian noise. Oh, yeah. So that I would say is an alchemy, right? In deep learning, people say deep learning is alchemy, which makes great sense. You have tuned your parameters, and someone tells you that, oh, I'm training a great model, language model uses this set of parameters. You should use this set of parameters, and in your case, it will fail. And so you have to analyze not too much, not too small, so something between. Yes, I don't have a universal guidance for this. I don't have. Yeah. But some people, I think they have some intuition about where to start. I think there's no mathematical guidance in this moment, but there's some intuition, some experience people accumulate from, like in computer science, they have some intuition, which is best to start. Thank you.